Good evening and welcome to the second of our Ian Ramsey Centre seminars on science and religion. It's on Thursday, the 16th of May 2013, and this is at Trinity College, Oxford. The title of tonight's talk is there a place at the science-religion table for mathematics? Our speaker this evening is Douglas Kindschi, who's University Professor of Mathematics and Philosophy and Director of the Kaufman Interfaith Institute at Grand Valley State University in Grand Rapids, Michigan, the United States. He's also Director of the Grand Dialogue in Science and Religion for the Greater Grand Rapids area, which is a Templeton-funded community local society which sponsors study groups and an annual conference. For over 20 years, he served as Dean of Science during the rapid growth period of this new state university, and he was responsible for the development of over 20 new degree programs, including a number in the health professions, as well as in the School of Engineering. Dr. Kindschi has presented on science and religion, as well as on interfaith themes throughout the United States, as well as in Europe. He's currently a visiting fellow at the Cambridge Interfaith Program in the Divinity Faculty at Cambridge University. So, would you please welcome tonight's speaker? Thank you.
Thank you very much. It's a pleasure to be here. I'm from that other place. You're allowed to use that word here, are you? Okay. And I'm also pleased to see so many people that come out to a talk that has mathematics in the title. That isn't often the case. But to rest assured, I'm not going to do a lot of high technical mathematics. I haven't done that much myself in the last many years because of my responsibilities as the Dean of Science and other responsibilities I've had at my university. But I want to look at mathematics and particularly at some of the philosophical discussion about mathematics and see if there are ways in which that can be a vibrant part of the science and religion discussion. So that's why I'm asking the question, is there a place for science and mathematics, or at the science and religion table for mathematics? Now, for many of you, since you've been involved in this, you're probably very familiar that physics, in particular cosmology, has been a very active part of the science and religion discussion. Biology, and particularly evolution, is a very significant part. And then recently, psychology, particularly the cognitive psychology and evolutionary cognitive psychology has become a very important part of the discussion. Relatively little has been said about mathematics. So I would like to introduce that topic and make the argument that there is a significant place for mathematics at the science and religion table. Let's start with the question of what is real. Religion claims that it understands and talks about ultimate reality. More recently, science has claimed that it is the only way that one can understand reality, only through the scientific method. But if you look at it historically, mathematics has probably the longest historical track record for the claim that it is talking about reality. Going back to Plato, who established his academy in Athens, and tradition has it that over the door it said, "No, let no one ignorant of geometry enter here." Now, why would he say that? Well, we get a hint of it in the Republic when he says, "The knowledge at which geometry aims is the knowledge of the eternal, not of the perishing and the transient." Then we come to Euclid, who was a student at Plato's academy and then went on to establish the mathematics program at Alexandria, and is famous, of course, for writing the Elements, probably the most successful math book, science book that's ever been written. In fact, last time I looked, I think it's outsold every book except perhaps the Bible, and was used pretty much in Euclid's form until about a century ago. Just to review our high school geometry, Euclid starts with 5 postulates and 5 common notions, and proves a series of theorems based on that. Now, the common notions for Euclid were pretty common, pretty self-evident. Things equal to the same thing are equal to each other. Equals added to equals give equals. Likewise, if you subtract equals, you get equals. Things which coincide are equal, and the whole is greater than the part. Nothing terribly controversial here, right? Then we move to his postulates or axioms. Again, pretty straightforward. 2 points determine a straight line. Straight lines can be extended. A circle can be drawn given any center, point, and radius. And all right angles are equal to each other. Nothing too astounding yet, until we get to the famous fifth axiom, which in Euclid's term reads as follows. If a straight line falling on two straight lines makes the interior angles on the same side less than the two right angles, the two straight lines, if produced indefinitely, meet on that side on which the angles are less than two right angles. Whole different character to that axiom from all of the others. In fact, it's almost very difficult to even understand it without a diagram. Is this a laser pointer?
No.
Oh, okay, all right. But what he is saying, if you look at the diagram here, is that if I have two lines, these two, and I intersect it with another line, and if the two angles, interior angles, sum up to less than two right angles, he's claiming that those two lines will meet at some point. Okay, the diagram helps us a little bit in understanding what he has to say, but doesn't make it crystal clear, like the other axioms, that this is a fairly straightforward thing. And sure enough, the fifth axiom was debated and struggled with for 2,000 years. And we'll get to that part of the story in a couple of minutes. We mostly today think of the fifth axiom in the terms that Playfair proved it in the 1700s, and that is, given a line and a point not on a line, there is one and only one line through the point parallel to the given line. That's the way most of us, I think, learned the fifth axiom. Well, starting with that fairly straightforward, simple beginning, Euclid proved 465 theorems, including things like the sum of the angles of a triangle are equal to two right angles, or today we would say 180 degrees. He proved the Pythagorean theorem, that if you take the square of the sides of a right triangle, it'll equal the square of the hypotenuse. He proved that there were an infinite number of prime numbers. All of this based on those common notions and 5 axioms. He proved that there are exactly 5 regular polyhedra called the Platonic solids. And I'd like to look a little more at this particular theorem. It's actually the last theorem in Book 13, the last book of Euclid's Elements. To remind you, a regular polyhedron is one in which each face is a regular polygon. In other words, all the sides are equal and all the angles are equal. And each vertex has the same number of faces and edges. There were 5 solids known at the time of Plato and Euclid. The tetrahedron, which has faces which are triangles and has 4 of them. The cube, which has regular squares for the faces, and there are 6 of them. And the octahedron, with 8 faces, all made of triangles. The dodecahedron, which has 12 faces made up of regular pentagons. And the icosahedron, which is made up of triangles, but there are 20 faces on the icosahedron. Those 5 regular solids known at the time of Plato, Euclid proved that that's all there can ever be. There can never be another one found, no matter how much mathematical research we do. The proof of that is fairly simple, and if there's time, if you want me to, in about 5 minutes, I've got some slides I can take you through the proof of it. It's available with very minimal knowledge and a very clever argument that he makes. But I want to look now for a minute at the science of Plato's time, because Plato, in his dialogue, the Timaeus, talks about the 5 Platonic solids. He doesn't call them Platonic solids. We call them that because he talks about it in this particular dialogue. And he relates it to what the physics of the day was, the 4 elements that make up all of matter. And those 4 elements at Plato's time was believed to be fire, earth, air, and water. Plato said that fire is made up of little tetrahedra, because they have sharp points, and fire breaks things up. The earth is stable, and so it, of course, is a cube. Air is the octahedron, and water is the icosahedron. and you'll notice there's one left over, and that's the dodecahedron, and he said that's the 12-sided zodiac that covers the whole universe. And this is all spelled out in the Timaeus. Not only that, he goes a little further and does what we would call chemistry. He says if we think of fire, and I'll put it in kind of a modern terminology, it's a tetrahedron, so let's call it F for fire, 4 for the 4 faces. Air, we'll call that A sub 8, because there are 8 faces on air, and water, we'll call that W sub 20. And he says if you take water and divide it by fire and air, you get 1 part of water, 20 faces, equals fire plus 2 parts of air. The 2 parts of air, of course, total 16 faces, and the fire adds the 4 to make it 20. So he balances the equations. Likewise, a volume of air can be divided into 2 of fire. Or 5 parts of air condense into 2 parts of water. So the physics and chemistry of Plato's day is kind of cute today. We kind of chuckle at it. It was ingenious, I guess, but science has gone way beyond what his science was. But the interesting part is that Euclid's proof still stands. Proofs in mathematics, once they've been established, aren't revised. Hermann Henkel says that in science we tear down the previous structure and build a new one. In mathematics we just add another floor. So this is one of the things that impressed Plato and philosophers actually for many, many centuries, with the idea that mathematics is true picture of reality, because the proofs establish them and they are not violated. Mathematics is the best and most certain description of the reality, was the sense that they had. And this carried up in through the science of the Renaissance. Kepler, in fact, was so impressed with the idea of the Platonic solids that his first attempt to explain where the various orbits of the planets were, what the ratio of those orbits were, he tried to explain that in terms of taking the various Platonic solids and circumscribing them in a sphere, and then looking at the ratios of the radii of those spheres. He thought that would be a model that would explain the orbits. He had to give that up, but my point is that even 1800 years after Plato, there was still an attempt to make the Platonic solids somehow be a picture of reality. Kepler, of course, revised his theory and did something that, given the Greek impact, was quite revolutionary. He said that the orbits are ellipses, not circles. Circles and spheres were considered perfect geometric objects, and they must describe the heavenly bodies. But he says, no, they're ellipses. Squash circles, if you will. And not only that, but he said that, again, violating the Greek idea that something would moved in space would have constant speed. He says, no, it's variable speed. And in fact, as the planet gets closer to the sun, it speeds up. And then it slows up as it gets further away from the sun, which is at one of the foci of the ellipse. But he also said that the area that is traversed, say during this period when it's closest to the sun, is the same as the area for a similar period of time, say a month, when it's further away. Now, why he would even conceptualize area about something that's in a three-dimensional, it's interesting. But that was what he said is constant, not the speed. But anyway, my point is that Kepler was influenced by the Greek idea, but not only Kepler, but others saw mathematics as absolute knowledge, as the best illustration of reality. He went on to say, the laws of nature are but the mathematical thoughts of God. Galileo is famous, of course, for saying the great book of nature can be read only by those who know the language in which it was written, and this language is mathematics. Newton, this is the most beautiful system of suns, planets, and comets could only proceed from the counsel and dominion of an intelligent and powerful being. This being governs all things, not as the soul of the world, but as the Lord over all. Philosophers and mathematicians like Descartes, I was especially delighted with the mathematics on the account of the certitude and the evidence of their reasoning. And even the great skeptic Hume said, Though there never were a circle or a triangle in nature, the truths demonstrated by Euclid would forever retain their certainty and evidence. So, for over 2,000 years, mathematics represented certain knowledge, the best description of reality, the language of science, in fact, what God used to create the world. God used mathematics to create the world. But then the big challenge came with the development of non-Euclidean geometry in the 1800s. Let's go back to those axioms that we talked about. The first four, pretty straightforward. The parallel postulate is the one that people said doesn't sound like an axiom. It sounds like a theorem, sounds like something that you could prove, like there's the sum of the angles of a triangle or an infinite number of primes. It has more substance and we should be able to prove it. And there were many, many attempts to prove it. But what finally developed from all of that is that three mathematicians in three different countries around the 1820s simultaneously discovered a different geometry, a geometry that said there's more than one parallel line, sometimes called hyperbolic geometry. Gauss in Germany, Bolya in Hungary, and Lobachevsky in Russia developed this non-Euclidean geometry that was perfectly logically consistent. Riemann, a few years later, developed spherical geometry in which he assumed that there were no parallel lines. And triangles in this geometry turn out to have more than 180 degrees. In the hyperbolic geometry, triangles all have less than 180 degrees. So, this certainty, this thing which is absolute certain and is the perfect description of reality, now we have three options, and which one is the correct one? Morris Klein, the historian of mathematics, says the importance of non-Euclidean geometry in the general history of thought cannot be exaggerated. Like Copernicus' heliocentric theory, Newton's law of gravitation, and Darwin's theory of evolution, non-Euclidean geometry has radically affected science, philosophy, and religion. It is fair to say that no more cataclysmic event has ever taken place in the history of all thought. A pretty strong statement. It led to a total rethinking of mathematics, which we sometimes call the foundations crisis in the early part of the 20th century. Logicism, developed by Bertrand Russell and Whitehead, tried to argue that mathematics was nothing but big, huge tautologies of logic. Intuitionism was proposed by Brouwer, but then fell out of favor. The one that seemed to have some currency for quite a while was formalism by David Hilbert, in which he says mathematics doesn't describe anything. In fact, he says mathematics is a game played according to certain simple rules with meaningless marks on paper. Boy, it doesn't make you want to be a mathematician, does it? He also said, geometry of point, line, and plane could be substituted by tables, chairs, and glasses of beer. He must have been in a pub or maybe in a Ratskeller in Germany when he said that. The point is that he was saying that it's meaningless. We could call them points, we could call them tables, we could call them lines, we could call them chairs. It doesn't really make any difference what we call them. It's just a game. It's just a game we play. So, what about mathematics in reality now? Does mathematics describe reality? Is mathematics just a game? Is it meaningless? Are mathematical objects real? Are numbers real? Points, lines, are they real? Recently there's been a rethinking of realism in mathematics. Martin Gardner, in his foreword to Roger Penrose's book, The Emperor's New Mind, says, Penrose has the courage to affirm a robust realism. Not only is the universe out there, but mathematical truth also has its own mysterious independence and timelessness. In referring to the famous fractal-like structure called the Mandelbrot set, Gardner comments that he, as well as Penrose, finds it incomprehensible that anyone could suppose that such an exotic structure is not out there as much as Mount Everest is, subject to exploration the way a jungle is being explored. Hilbert was reacting against the radical realism that mathematics is the only really statement of what is real. And now The counter to that has been a rethinking and a restatement of realism. Now, realism in science, Putnam at one point said that realism is the only philosophy that doesn't make science, the success of science, a miracle. He's given up that attitude now, but that was a famous statement of his. And it is an interesting point. If you don't believe that science is actually touching reality, isn't somehow making sense out of reality, then why is it so successful? I would ask another way, if mathematics is nothing but a game, why don't we use chess or soccer to explain our science? You know, is there something going on here, as Putnam says, that is related somehow to reality? So I want to look at that. The success of mathematics in the natural sciences is something bordering on the mysterious, and there is no rational explanation for it, said Norbert Wigner, who wrote a famous paper called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He goes on to say the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. So he's saying, I don't understand it. It just must be a miracle. Putnam's argument would say, there's too much success there. There must be something else going on. So we need to keep unpacking this question of what is the nature of mathematical knowledge. Realism can also be approached from another direction. We could talk about realism, as some do, is what was there before humans existed? Most philosophers would say, well, rocks and mountains and trees existed before humans existed. Probably would go on to say molecules and the moons of Jupiter and electrons existed, even though we hadn't discovered them, maybe, hadn't been discovered. But they would say that things like chivalry and politics and grammar are just human inventions. They don't have ultimate reality. So let's look at science as objective. Science is objective in part because it lets the object tell the scientist what's going on. It doesn't take what the scientist wants to believe and make it part of that. It says, let the object tell us. If, for example, I was a scientist and I was studying bats, I would set up certain experiments and let the bat tell me what the answer is. I might notice that they have very successful flying patterns, so they must have incredible eyes. And then I notice they don't seem to have very well developed eyes, and in fact they do just as well at night as they do in day. But then I notice they have large ears and they make squeaking sounds, so I might cover up the ears and do experiments. And I do experiments with the object and let the object inform me as to what the reality should be. Science is object-oriented, and in that way argues for its own objectivity. But is mathematics objective? Do mathematical objects exist? Do we do experiments with numbers? Do we try to let them tell us what they are? If they exist, where do they exist? Do points and lines exist? Are they objects? Have you ever seen a point? Have you ever seen a line? I do this with my math students. I put dots on the board and say, what is this? And maybe a streak across there. They say, those are points, those are lines. I says, no, you've never seen a point. A point has 0 dimension. It's impossible for you to see a point. You've never seen a line. Line has only 1 dimension. It's impossible to see a line. You're only seeing representations, or if you prefer, even metaphors of lines and points. So, in what sense is mathematics objective if we've never seen the objects of mathematics? Well, a recent development in the philosophy of mathematics called structural realism takes an interesting turn. In mathematics, this is from Michael Resnick, in mathematics I claim we do not have objects with internal composition arranged in structures. We have only structures. The objects of mathematics are structureless points or positions in structures. As position in structures, they have no identity or features outside of the structure. I will then argue that structures existed before there were humans. If rocks and mountains and trees existed before humans, structures existed before humans. Structure is real. Relationships are real. Reality is matter plus structure. And the physicalists would sometimes forget the structure part of that combination. An oak seedling and a fully developed oak tree, while they have the same DNA, are different in relationship. There is a relationship difference there. They're different in size. They're different in their structure. There's a difference between oneness and two-ness. If I have one rabbit, that's one kind of reality. If I have two, I may end up with a whole lot of rabbits. That structural difference between oneness and two-ness is real. In fact, it goes right down to the depth of the biological cell itself and the DNA structure. The DNA structure is a two-ness structure. It's a double helix. And when it replicates itself, it unwinds and creates the appropriate bonds to make a new double helix. So the two-ness is a very important part of this very structure of biology, and the one-to-one relationship of those bonds are very important parts of the structure. Or if I have a group of students and a group of chairs in a classroom, if there are more students than chairs, someone doesn't have a place to sit. This concept of one-to-one relationship is a structural thing that is true. Young children, before they know how to count, can tell the difference between a small number of M&Ms and a whole pile of them. They don't have to count to know that difference, or to know the difference between a small piece of cake and a big piece of cake. Before they studied mass and density and volume and all of that, they know that. So my claims are that reality is matter plus structure, and structure is based on relationships. Matter is real, but structure is real. Now some philosophers and people that are working in this field talk about the hierarchy of the sciences. And they say we have sociology, economics, and politics, which is based on our understanding of psychology, and that is based on zoology and physiology, which in turn is based on cell biology, biochemistry. There's this desire to reduce these various hierarchies to a lower level. Biochemistry based on physical chemistry, based on atomic physics, nuclear physics, particle physics, this hierarchy. What we also notice in this hierarchy is that as you go down the hierarchy, the objects of observation are smaller and smaller and smaller. But at the same time, there's increased certainty. The ability to predict with quantum mechanics is one of the most highly developed models. And nuclear physics is more certain than cell biology. There tends to be an increased certainty as what you're looking at gets smaller and smaller. Well, I would like to suggest that not only is there matter plus structure, but there's structure alone, and that mathematics belongs in this hierarchy as that yet even smaller field, the area that deals with structure only, not matter. So, mathematics is structure alone. It studies structure without objects. It has the highest degree of certainty, but is it objective? It's not object-oriented, I've already mentioned that, but in what sense can we say that it's objective? Well, the mathematician J.R. Lucas has argued in his book, The Conceptual Roots of Mathematics, that mathematicians are not in fact concerned with a disparate set of entities, each on its own, but on patterns whose structure is what is the essential part of their being, what they are. And those interrelations with one another could not have been different. Then he goes on to say, realism that is more concerned with objectivity than objects. It is a realism whose non-subjectivity is based on rationality rather than on opaque thinginess, matter. The reason why mathematical truth is hard and ineluctable is not that it is a quasi-material object, which stands in the way of my getting past it and blocks my effort no matter what I do, but that as I come to more and more understand what is at stake, I see I would be acting unreasonably to deny its truth. In this sense of objectivity, then, we can argue that mathematics is objective, not object-oriented, but is objective. It's unreasonable to deny the truth that we discover here. Mathematics provides a structure or a lens in which we view and make sense of empirical data. We all know about Galileo discovering the moons of Jupiter. We discovered that the moons existed. But so did his telescope. And so did not only the moons were real, but the structure of the glass lens was real that enabled him to do that. The mathematics of optics are also real. So the mathematics allowed, the mathematics of optics, the mathematics of that telescope allowed Galileo to see another part of reality, namely the material moons of Jupiter. So I'll add another claim, and that is that mathematics is a lens that helps us make sense of the physical world. When we look at our empirical data through a mathematical model, things fall into place. Things start making sense. And in fact, scientists say that this is a standard pattern. That if you have a beautiful mathematical structure, there's a fair chance that it may be what you're looking for. And quite often, say if you've got a group theory model and there's a piece missing, you look for that piece because the mathematics implies that that piece should be there. I want to make another claim, and that is that structure is non-reductive. We don't understand natural numbers by the careful study of 3. We don't understand a triangle by studying the points. You need the whole structure. You can't break it down into its component parts. Not only is mathematics non-reductive, I would argue that language and meaning is non-reductive. I may have a number of marks which are not particularly meaningful to me, but the same kind of, whether it's ink on a page or pixels on a screen, can be recognized as letters. I don't recognize them by reducing them to the pixel. It's the structure, it's the pattern that creates that meaning. Or I might recognize, excuse me, I might recognize repetition or order or even words. And I don't reduce the words by looking only at the letter, and that's going to tell me what the word means. I'm suggesting these are non-reductive steps. Concepts, sentences, statements, physical laws, moral principles, philosophical claims. All of these at the material level, whether it's ink on paper or pixels on a screen, all of them are the same at that material level. What makes them different, what gives them meaning, and what gives them these levels of meaning are the structures in which those material objects exist. It's the structure that's the key here, not the matter. Not in the ink spots, the meaning, but in the structure, patterns, and relationships. We don't understand Shakespeare better by analyzing the chemical composition of the ink and paper. So I would add one more claim. Mathematics is non-reductive. I want to pursue a little bit further this topic. Euclid attempted to define points and lines in his Elements. Excuse me. In his Elements, he said, a point is that which has no part. A line is breadthless length. A straight line is a line which lies evenly with the points on itself. Well, does that really help? Do those definitions really help? It's the classic dictionary dilemma. When you look up a word, it uses other words. You look up those words, and eventually you'll get back to the word you started with. Or if you look at the Oxford Dictionary, it defines a dog as a domesticated carnivorous mammal of the genus Canis. Well, the problem that finally mathematics realized is that you can't define all your terms. We begin in mathematics with undefined terms. The terms are defined relationally. Point takes on its meaning because of the relationship of points and lines in the axioms. It's a relational definition of the word terms, not an explicit definition. So, basic terms are defined relationally. One more thing I'd like to point out, and that is physical instantiation. Pattern, structure, and can have various instantiations in various physical forms. And the digital world has given me, I think, a nice way of illustrating that. I have a picture here, a picture of my grandchildren. I have a relationship with them, but this picture makes sense because of the relationship of the pixels. Picture's gone, right? No. It's instantiated now as pixels. Now it's gone. Nope. It's on my flash drive. It's on the hard drive. Structure can be instantiated in multiple material physical ways. And I think that's another important thing that we've discovered and learned about how mathematics and structure relates to the physical world. So, adding a ninth point to my further claims, structure can have multiple physical instantiations. Now I want to come back to the question, what is the role of mathematics at the science and religion table? Is religion or theology mathematical? Do we prove theorems? Can we claim rational certainty? No, that's not my claim. I do claim, however, there are useful similarities and even metaphors that we can use as we understand mathematics and unpack how mathematics functions in our understanding of knowledge and science. Let's look again at mathematics at the table. It's not empirical, we don't see points. The definition in terms of relationships. It deals with relationships and structures, not objects. It's objective but not object-oriented. It's non-reductive. It expresses something real. It opens to multiple instantiations, and it serves as a lens which focuses the structure of the experienced world. I would like to suggest that religion has those same characteristics. It's not empirical. We don't see God. Theologians have tried over the years to define God. It doesn't get us very far. In fact, some would say it's impossible to define God. But we can talk about God in relationship terms. In fact, it's interesting. I think that many of the metaphors that are used in Scripture and elsewhere are relationship metaphors. The shepherd, the king. These are relationships that are being defined. God is defined relationally. Deals with those relationships and structures, not the objects. It's objective but not object-oriented. It's non-reductive, but expresses something real. It opens to multiple instantiations, and it can serve as a lens which helps focus the structure of the experienced world. Phil Clayton, in his book Explanation from Physics to Theology, says, "My thesis is that religious beliefs are grounded in the onset in their ability to make experience of the individual and group meaningful. The believer understands the world in a certain way. That is to say, he perceives a significance in certain or all objects or situations that others do not." I want to take one more tentative step in the relationship, and this is related to my current and fairly recent responsibilities in directing an interfaith institute. And I've been trying to think about how to understand that. And I think that there is maybe a connection here to mathematics. In mathematics, we study various multiple systems. And we have geometry and topologies that are Euclidean and hyperbolic and spherical, various algebras, group theory, field theory, various number systems. We don't ask which one is true. We ask which one makes sense and which one is applicable in making sense of our experience of the world. Could it be a model for looking at the various religious traditions? Is it possible that the religious traditions are in their own way models that are trying to make sense of the world? Most of us would say that as humans, we don't have a God's eye view. We must have a certain amount of humility of how much we really understand. Could it be that the multiple religions operate with different systems, but the question is not which one is true and which one is false. The question is, what is being explained? What is being understood? To what kind of meaning does one tradition bring to us? And if it is meaningful for one person and is making sense for them, is it important that we try to tear that down and say that they're wrong? We wouldn't do that in mathematics. We don't have geometers saying that the algebraists are all wrong and shouldn't exist, should be destroyed. Is that a possible? And I ask this as a question, not as something that is very well thought through yet, but it's something that I'm working on. So let us bring mathematics to the science and religion table, and let's see what we can learn from each other. And in the words of J.R. Lucas, as I come more and more to understand what is at stake, I see that I should be acting unreasonably to deny its truth, the truth of mathematics and the truth of religion. Thank you. It's question time, right?
Yes, we have, I think, after about half an hour, maybe slightly more for questions. And my colleague, Dr. Silver, will bring a microphone round. If you want your question to be recorded, please wait until the microphone reaches you. Thank you.
So, thank you for the talk. I just had a couple of questions from the perspective of someone who's a practicing mathematician. You seem to have a slight contradiction in what you're saying. You're saying that mathematics is both not empirical, but it is instantiated empirically in a form of realism. That to me seems to not be completely coherent as a pair of statements. And I wonder whether you'd be better off thinking in terms of mathematics as structure, as you suggest, but its relationship to reality being in terms of a model. That we don't expect this to reflect reality perfectly, but it gives us understanding, gives us representation, it shows us things, but we don't expect a perfect correspondence. I just thought you might like to comment.
Yeah, I accept what you've said. I think that's right, that mathematics serves as a model. I also use the imagery of a lens. Looking at something through the mathematical lens brings things into focus that may not have been in focus without that mathematical system. When I talk about structure can be instantiated in multiple physical forms, I'm not trying to make that I'm trying to just point out that's something about structure. The structure doesn't have to always be in a particular physical form. It can have multiple instantiations. I'm not trying to make that as the argument for realism. That's something that I argued afterwards. I would argue that let me put it in other terms. There are those who are Platonic in their understanding of mathematics. There is another world, a world of mathematics, and then there is the material world, the world we live in. I'm rejecting that approach. I'm saying, okay, you got this Platonic world. Roger Penrose has three worlds. He has the mathematical world, the material world, and the mental world. Another person I've been working with has 5 worlds. I get nervous about the multiplicity of worlds. I would like one world. I would like one reality. I would like us to understand as best we can a single reality. So what I'm arguing that would be different here is that the one world that we're in is made up of matter and structure, but structure is more fundamental. It is more fundamental than matter. All through the system, it is a combination of matter and structure, but mathematics is examining that part of the real world that is the structure without the matter. And it is opening up what I would call possibility spaces for matter to exist. I hope that helps.
Thank you. You said that electrons would be one part of science that we would generally say would preceded the existence of humans. But let's imagine that science moves on and in some future date we come to disbelieve in electrons. We would then have to say, there was a period when electrons were thought of as real but turned out to be a human invention. Perhaps take a better example, phlogiston. which was believed in for a short while, but then disbelieved. Is there anything in mathematics which might be like that? Anything in mathematics which you might say is a purely human creation?
Well, that's a complicated question, and let me approach it, try to unpack it. There's no question that there are aspects of mathematics that are humanly created. The language we use, for example, is a human creation. The axioms we choose to develop our structure with is a human choice. What's not human, I would argue, is the implications of those axioms. You know, as was pointed out in the history of mathematics, the fifth parallel postulate was a choice that Euclid made, a choice that later Lobachevsky, Bolia, Riemann, others chose a different axiom. What is not chosen, which is objective, are the implications of those axioms. So the language we pick, the language we choose to use, whether we call them points, I mean, just if you look at the different languages we have, we have different words for these things. The axioms that we pick are human choices. The structure that emerges from that, however, I would argue is reality. Now, can we be wrong? Obviously, we were wrong about phlogiston. We may be someday wrong about electrons. I'm not claiming that humans or mathematicians are infallible, but I would say the track record for mathematics is pretty good. I mean, Andrew Wiles proved the Fermat's last theorem, but then found out when he was explaining it that there was an error, and it took him another 2 years to find the error. So yes, we can make mistakes, but I would just argue that mathematics has got a pretty good track record.
Thank you for your talk. Do you think that Kurt Gödel's incompleteness theorem undermines at all your notion of mathematics as being a structural basis for reality? If it's true that a system is incomplete, or if it cannot be complete and consistent at the same time, does that not mean that a mathematical understanding as the basis of the universe is going to be insecure, and therefore it couldn't be real in that sense?
I think it undermines Hilbert's program without question. Hilbert argued that the only thing we can claim for mathematics is that it's consistent and that it's complete. And for those of you that aren't familiar with this language, consistent I think is obvious. There aren't any contradictions in it. Completeness means that any true statement in the system can be proven from the axioms. And what Gödel proved is that there are statements that we understand to be true. We know that they're true, but they are not provable in the system. That has no impact on my argument, because I'm not arguing that mathematics is a complete system underlying reality. I'm not making that argument at all. I don't even, it's possible even that someday we would find contradictions. What have been apparent contradictions in mathematics, we've worked our way around. The famous Russell paradox, for example, and found ways to avoid those. So I'm not claiming that mathematics is complete, and therefore, and it has to be complete in order to be foundational to the rest of reality. All I'm claiming it is more certain, the rationality that it uses, and that it does in fact provide a base for much of what we understand in the material world as well. But it's not required that it be complete. In fact, I would argue probably theologically that generally humans don't have complete knowledge. And so I actually theologically relish Gödel's proof.
I suppose there are two different kinds of mathematics. Mathematics of nature and mathematics of humans. Human mathematics is kind of more simplified. For example, we can use PDA or a different kind of equation to describe kind of flight of bats, but real flight of bats connected with more sophisticated, more difficult, more profound mathematics. We cannot describe very simple equation of our hands. It's very difficult. It's very, very difficult. This means that there are difference between human mathematics and mathematics of nature. And human mathematics, it's just only approximation. What do you think? And Gödel, you made reference of Gödel. Gödel, there is a two different kind of statement. Gödel suggests about completeness of mathematics of nature, but not humans. What do you think about this?
Well, certainly the mathematics of nature, just like the physics of nature and the chemistry of nature, is not completely understood. You know, human science, the human understanding of these things are always incomplete. So, yeah, obviously, we don't have a complete mathematics for nature. In fact, it's very interesting that when we do develop a new mathematics like fractal theory and Mandelbrot's work, that we find reflections of it in nature. And we also have a tendency to look at nature through only certain rational views, certain. You know, in the case for a long time, we always wanted things to be mechanical. We wanted them to have kind of a mechanical relationship, probably because of the impact of the clockwork universe that we got from Newton. But as our knowledge grows, we find that some of those things were not complete descriptions of nature. So what I would say is what we're discovering in our human mathematics is that there are structures that we didn't understand before. And as we explicate those structures mathematically and they become useful for science, we're making progress in that area. But I don't think it's necessary that we think that it's all done at this point.
Thank you for your talk. It seems that you are claiming that mathematics and religion are both lens to understand the world. And I think that Descartes, in a way, who was a mathematician and a philosopher, helped us to understand this, and some philosopher and theologian are using Descartes. But my question is, if it is so, where is the place of the intervention of God in the human freedom to understand the world? Because I think mathematics is more something created by a human mind or rational human mind. But religion could be, we can apply mathematics in religion, I agree with that. But it seems to me that there is the intervention of God in the human freedom to understand this, what you call the lens, to be able to understand the world. What is your response to this? Thank you.
Yes, absolutely. Would never suggest that mathematics does not make important or necessary a theological understanding. In fact, I'm making precisely the opposite argument. What I'm saying is that mathematics and the way in which we can look at that and its relationship to other knowledge can even be used as a model for our understanding our religious understandings. That we don't need to have our metaphors and the science religion discussion only coming out of physics and biology and those kinds of fields. That mathematics should come to the table and provide some models, some metaphors even, for how we conceive of God and understand God. So absolutely, the religious part of this is basically my whole point, and that is that we need that religious understanding. And furthermore, maybe the insight that we get religiously can be improved by understanding how mathematics functions.
Can maths be used to explain consciousness, which is a very important aspect of life on Earth?
Ooh, that's not only a very big question, but it is a very controversial question. I think we talked earlier about Thomas Nagel's book. There are certainly people like Nagel who would argue that our current understanding of material evolution is not adequate to explain consciousness. He may be right, I don't know. Would I claim that there are current mathematical structures that will explain that? I have no idea. Very, very possibly not. What has happened in the history of mathematics, however, is that the mathematical exploration of structures have later turned out to be exactly what the scientist needs. So if I were to make a wild prediction into the future on consciousness, if we ever do understand it, and I think that's a big if, can, as a biologist Haldane said, is the human mind complex enough to understand the human mind? If the human mind were simple enough to understand, our mind not be able to understand that. I mean, there's almost a circular problem here. So I don't want to make any claims there. There's a lot of people working in that area now, but what I would say is that if it was somehow a scientific explanation for it, I wouldn't be surprised. But what the mathematicians had developed some of the systems that were important to that.
Can I just go a further point here? Certainly from a perspective of ignorance, only having an O level in arithmetic, but people, would you say that quantum mechanics was a mathematical problem rather than a problem of physics? And then we get into wave theory and wave collapses. How does that relate to even consciousness? Because people are trying to say that consciousness is a quantum kind of sort of thing.
I'm familiar from the outside with some of that literature. I'm not a particle physicist or a quantum physicist. All I would point out, as I understand it, is that level of physics does in fact use mathematics to make sense of what they're doing. But whether that relates to consciousness, I don't know, and I don't know if anybody knows, frankly.
Yeah, you can study nature, which is material, through mathematics, but our Father God is supernatural, which you can't study through mathematics. For example, miracles, and at Pentecost, everybody listened in his own language. So you think you can still explain supernatural through mathematics?
No, I don't think I can, nor do I think I claim that I could. I don't make that claim at all. One question.
So you had a table that showed mathematics down at the bottom and matter and structure, both constituents of reality, but structure is fundamental.
Right.
I wanted to push you one level lower than that.
Okay.
A continuous versus discrete, digital versus analog. Do you want to speculate on whether one of those is more fundamental than the other, or is there a parity between them?
Well, I mean, at the time that Newton developed his continuous methods, which of course calculus and analysis all assumes continuous processes, we didn't even know there was a finite universe, scientifically. We may have predicted that from Scripture, but we didn't know it scientifically. So now that we know there's a finite universe, you can actually estimate how many particles there would be at a finite universe. So the question is, does that undermine a continuous understanding? I don't think so. I think that both, frankly, are, if you will, sets of axioms, sets of assumptions, both of which have turned out to be extremely valuable in understanding. So I guess if you're wanting to push me, and I haven't thought about this, but if you wanted to push me, I would have to argue that both discrete and continuous are real structures. But there certainly is a case that could be made for discrete structures being, at least as we understand things now, being primary. Whether that'll work or not. But even with discrete structures, even things as simple as the natural number system, we can talk about numbers. In fact, we now prove prime numbers and prove various theorems that go numbers that are way beyond anything we experience in nature. We can talk about those things. Does that mean they're not real? No, I think they are part of a structure, an infinite structure. There is an infinite structure underlying this, even though we live in a finite material world.
had an idea with which I think you might be able to bolster your arguments, essentially by kicking up some dust around the idea of what's empirical. To take a Peircean angle, I think you could assert that certain things that are standardly empirical are about as non-material as something like the number 3. For example, take the blueness of the Ian Ramsey Center banner over there. Blueness is a quality, and qualities in themselves just do not happen. Things that happen are brute facts, like bumping your head up against something, or say encountering that banner with its blueness and whatever else it has. What I mean is that quality is just a qualitative possibility. I think I don't think it's of the same kind of realm of reality as what you might call actuality. And Charles Peirce, whose system I'm more or less thinking in, thought that mathematics is of the same realm as qualities. He called it firstness, which he contrasted with secondness, which is this kind of actuality thing, and thirdness, which are things like laws of nature and rules. So if you contend the actuality of a lot of empirical reality, then you could justify the place of mathematics as real in those terms.
Yeah, I'm impressed with a lot of C.S. Peirce's ideas. But I think you've also brought up another issue, and that is the difference between accidental and essential characteristics. And I would not want to argue that mathematics is like color, because color is something that you could argue is something that is the way in which we interpret the frequencies that are going there. You could make an argument that color is not real in the sense that it didn't exist before humans. I would resist putting mathematics in the same characteristics as accidental qualities.
But you also might want to resist putting it in a kind of atomistic framework at all.
Well, I might, but I might not.
Where your thoughts taking you now?
Yeah. Well, where my thoughts are taking me is a resistance from the multiple world thing. I'm really bothered by what seems to be the new realism. The new realism is a return to a Platonic world. And I'm bothered by that. First of all, if the Platonic world is a separate world and a real world, if numbers, and I've heard theologians at major lectures say that God and mathematics are eternal. Ooh, I don't know if I like that. I don't like that same category. But so I'm trying to bring mathematics into the real world and give it not to demote it from this Platonic world, but to give it even more reality, because I think that Platonic world has problems in itself. And especially when you get 3 worlds and then 5 worlds, I mean, where does this stop? And what does it really help us understand? So my desire is a kind of a monism, to try to get a single world and our understanding of that single world into some kind of a configuration that makes sense. And then what I find interesting is when I do that, it also helps me understand theological terms. You get to question 2.
I get a question too. Okay, so I was curious, what do you think about the realism of numbers for which we have a rule of construction, but we can never actually construct them or find them? So, for example, there may be a number which is the number of digits at which pi has 1,000 zeros, but we've no idea where that is. We have a rule for generating, for finding the number, but we may never find it. What about the Mandelbrot set? Take an example, which never repeats as a pattern that never repeats itself. Presumably, what would you think about the realism of if it was expanded to 10 to the power of a billion? But we can never actually build a computer within this physical universe able to generate the accuracy required to produce that pattern. What do you think about the realism of things like that?
Well, of course, that's the argument that Brouwer and the intuitionists brought up. That I don't accept that for a number of reasons, and I'm not alone. The mathematical community in general has had great difficulty with constructivism. I guess I would, I still believe in the law of the excluded middle. I mean, something is or it isn't. And especially in mathematics, when you're dealing with something that is so thoroughly rational and logical, I would say that either they're in the expansion of pi, either there is a sequence of 100 or 1,000 zeros, or there isn't. That is, I would say ontologically, it's one way or the other. Epistemologically, I have no idea, and we may never know. And I guess I would say the same thing about our understanding of theology and religion. There are things which we can affirm ontologically, but we can't epistemologically say why we know that to be the case. And in fact, in another talk that I give, I talk about courageous humility. We need to be courageous in our ontology, in what we believe to be true. We need to state firmly what we believe to be true, always recognizing that we could be wrong. And that's the humility in our epistemology. So yeah, we make these claims, and I would make claims in mathematics that would not be constructivist claims, but recognize that epistemologically we may never know.
We have a couple of minutes left, or we could call it a halt, and the speaker will be around for a few minutes. Any final questions?
I'm just pleased that so many people show up for a talk about mathematics, and there's so much good discussion. I think that's really wonderful. Most people, when they ask what I do and I say I'm a mathematician, they want to change the subject. So thank you for being a very good audience.
Well, just before we conclude, then I'll make a brief announcement for our next and final talk for the year. It'll be on the 30th of May, and it's Dr. Thomas David Barrett, who is who's in the Social and Evolutionary Neuroscience Research Group here at Oxford, and also a fellow and tutor in economics here at Trinity College. The title of his talk on the 30th of May, 2 weeks' time, is Collective Action, Shared Intentionality, and the Origins of Religion. So I invite you to join us then. Would you please now I'd like to conclude by inviting you to join with me in thanking our speaker this evening. Thank you.